Thank you everyone for coming to our seminar today. So it's our pleasure to have Aurelien Sagnier from Johns Hopkins University. He will tell us about towards arithmetic sites at some places. So please.
Thank you very much for the introduction, and thank you for the invitation to speak at this seminar. Although I must apologize first because I know it's a non-commutative geometry seminar. There will not be much non-commutative geometry techniques, although I mean it is still in the air. I mean, because you are dealing with the Adel class space, and somehow the constructions are, I mean, there are hints, and for some parts it has been discovered also by Kohn and Consani that it is linked with Boscone system and so on, but it's still, at least for me, unclear, or at least it's a collection of hints, and it's not properly written yet, so I will not focus on the non-commutative geometry, but I will, my goal is rather to talk about those arithmetic sites that you may have heard of, especially the one of first Kohn and Consani, and then what I tried to build. And I mean, the purpose, but you will have to tell me if at some point I'm going too slow. My point is that the constructions in itself of the arithmetic site of Kohn and Consani, as Kohn once told, it's understandable by a child somehow, and what I did, it's only referring to complex numbers and polygons. I mean, and hence it's this drawing of the movie Dimensions. I don't know if you know it, which introduced complex numbers for early undergrads. So the constructions are in fact very simple, but what is not is to understand why we bother about such things, and I will try to really put much emphasis on the context, but if the context is already clear to you, please tell me, and I will move more quickly to the constructions and so on. So first, so we are doing, we want to do arithmetics, and a very powerful set of analogy in arithmetics is what was called by André Weil the Rosetta Stone. Is one of his papers in the second volume of his collected works. It's about mathematics and metaphysics, and it's the following. It says that somehow in arithmetics, at least in the 20th century, you had it looked like you had a kind of Rosetta Stone with 3 languages. First was the Riemannian languages, so dealing with compact Riemann surfaces. A second column, which we called Galoisian, which was dealing with curves over a finite field, and then the arithmetics, dealing with number fields. And going back and forth, those languages was really fruitful in the history of arithmetic geometry so far. For a great part of the 20th century, I mean, for the building of algebraic geometry as we know it now and arithmetic geometry, the task has been to import technologies that were already existing for compact Riemann surfaces into this context of Galoisian language somehow. For example, like cohomology, I mean the techniques of sheaves of cohomology, and so on and so forth. And of course, it's so it's a powerful set of analogies, and you may know that here in this column somehow mathematicians beginning with Artin at first, then Hasse, Weil, and so on, were able to attach a zeta function to a given curve, to curves over a finite field. And then the question was, okay, for those zeta function, one can formulate the analog of the Riemann hypothesis. And okay, for those functions, are you able to solve the Riemann hypothesis? In fact, the question, the answer was yes. So here I reproduced part of kind of what you would say the Kohn and Consani vision. I mean, in their program and the way I understand it. And I mean, they probably have a more subtle way of saying that, but what I understand from their program is that, okay, so in the Galoisian language, so it relies on works of Artin, Hasse, Weil, Grothendieck, and many others. You take a smooth projective curve over a finite field, then you are able to define a zeta function associated to this curve. So it really looks like an Eulerian product. And so it mimics the definition of the completed zeta function. I mean, the usual one where you have the product over the primes, and then this infinite factor and that enters when you want to have a nice functional equation for the Riemann zeta function. And what people found in this Galoisian column, which is, if you want, algebraic geometry or arithmetic geometry, is that one can also define another kind of zeta function. The two are related by this relation. And what is interesting here is that the logarithmic derivative of this newly defined zeta function, this one is called the Hasse-Weil zeta function, by the way. So this logarithmic derivative is in fact the generating series of the number of points of your curve over FQN. So if you see your curve locally as a set of a system of polynomial equations, then you look at the set of the solution of your system into this FQ to the n, and then you take the generating series of the solutions in FQN as n tends to infinity. And the really striking feature that relied on the work of Hasse first in some cases for elliptic curves, but then Weil, and then really put in a kind of definite and stable manner by Grothendieck, is that the geometry that exists when you talk about curves and so on, and in fact, this geometry that they developed came from the adaptation of what happened for Riemann surfaces. I mean, concepts that were already existing for Riemann surfaces, but they adapted those in the context of curves, I mean, smooth projective curves over finite field. Once you do that, then you are able to solve to prove the Riemann hypothesis for the zeta function associated to your curve. So it's really striking, okay? And what Kohn and Consani did, they tried to see if somehow one could draw a parallel in arithmetics. So when you take this completed Riemann zeta function, then they found that the logarithmic derivative is somehow, I mean, it looks close, but here in the case of arithmetic, it's more complicated. Here it will not be just a series, it will be an integral of something, I mean, much more intricate. It's a distribution that comes from analysis on the Adel class space. So the natural question when you look at this set of analogies is, okay, are we able in the arithmetics column to find a geometrical background for this analysis going on the Adel class space? And the answer, I mean, the arithmetic side is part of proposition of answer. I mean, will it be will it give the solution for proving nice things like Riemann hypothesis? No one knows so far, but it's a solution. So yes, here it's just a reminder if you are not familiar with the Veil conjecture and what happens in the Galoisian column. It's just that it's a way to say that the Veil, I mean, what is called the Veil conjectures for those curves somehow. It's really so it's to say that this function whose logarithmic derivative is the generating series of the number of solutions. It's just a rational fraction, and you impose something on the, I mean, you know precisely the denominator, and you impose something on the numerator. And what you impose here on the roots of the numerator, in fact, when you transform back to the zeta function given as an Aurelien product, it really says that all the zeros of this function associated to your curve is on the line real part of S is equal to 1/2. So it's really clearly an analogous of Riemann hypothesis. And just here, few sketchy way to explain how the geometry helps you in order to prove the Riemann hypothesis in this context is that when you want to prove this, so it's an assumption on the roots of the numerator of this generating of this function whose logarithmic derivative is the generating series of the number of solutions, is that the Riemann hypothesis is equivalent to this asymptotic estimation of the number of solutions. And it's really funny because in arithmetics, the true actual Riemann hypothesis is also equivalent to some kind of asymptotics on the number of primes that are less than a given number. So what do you do to, so now people, well, at the time to prove the Riemann hypothesis, then they said we will prove this asymptotic estimation. And to prove that, well, they noticed that the solutions of the point of your curve, so the solution that are in FQN, it's the fixed point of the Frobenius, which is iterated in n times on your curve somehow, but it's your curve extended to the algebraic closure of FQ. And then once you interpret your points in FQN as the fixed points of the Frobenius, then you can say, okay, how do I compute the fixed points of some operator? Well, it's a basic fact that when you have a function, for example, you want to look at the fixed point of the function, it will be just the points of the graph of your function, which are also on the diagonal. And here it's just what it tells. It's somehow if you want to do it, if here you have your curve, you have your curve as well. You have the diagonal, and here you look at the fixed point of the Frobenius. Here you say it's the graph of your Frobenius iterated n times. Then you look at the fixed points. Okay, I mean it's a sketchy way to represent this. And okay, so now you are left in trying to compute the number of intersections of two curves on the surface made by your curve, the curve you started from by itself. And that it's a geometrical problem, and you solve it by saying that in fact the intersection form on your surface is a quadratic form of index 1, and then you decompose carefully, and you use Cauchy-Schwarz, and then at the end you are able to prove this this asymptotic estimation. So it's really striking because once you have found, and it was really hard, and it was the work of all those great mathematicians up until Grothendieck, to define the geometrical context, but once you have the geometrical context, it's just an exercise on quadratic forms. So it's really striking. So of course, now one would like to find a geometrical context here for in arithmetics. So okay, we want to find the geometrical context so that we can say somehow this zeta function is attached to a kind of curve or geometrical object or whatever it is. So here I'm just, yeah, maybe I will skip on this. It was just to recall how Kohn gave a spectral interpretation of the zeros of the L functions. I mean, you probably know that already. It's just somehow in order to explain how this n enters into the picture and how this Adel class space comes into the action, but it's technical. I will skip quickly, but here somehow it's the point is that when he was able to prove this theorem is in 1995, somehow, so okay, thanks to analysis on the Adel class space, he was able to get a spectral interpretation of the zeros, but then it was very complicated at the time to see how just with analytical tools to get something more on the zeros, to be able to say something more precise. In fact, maybe this some hope, there's still some hope, because you can see at the latest article where they refine the techniques and use Sonin spaces, and okay, they don't solve all the questions, but maybe there's a way when you use to use analytical tools in order to get closer to a solution. So, but it's the article that was published 1 week ago, I guess. But okay, so far in the program, even if in this article there is inspiration given by the geometry as well and so on, but a main part of their approach was to get a geometrical understanding of the ideal class space. Okay, so while looking for that, they found the arithmetic site, but and I will tell you what it is soon. But what I can already tell you is that somehow, the arithmetic site is something of tropical or characteristic one nature, which sounds weird. Why would you want something of characteristic one? What is even characteristic one anyways? So, okay, I will try to give you a reason why okay, characteristic one, it's not so weird as it looks like at first. It just comes from an idea which looks like a Maslov dequantization process, where you put the parameter h as log p. It's that somehow in the 90s, Christophe Soulet wanted also to understand more of this arithmetic column, geometrical context around that. And then he said, well, we will say have a notion of scheme over F1. So it will be a scheme defined over the integers. So it means locally, locally it will look like the set of the solutions of a system of Diophantine equations. So I mean polynomial equations with coefficients in Z, but such that there exists a polynomial, so big N, with integral coefficients, such that this polynomial N interpolates something which is the number of solutions of this system of Diophantine equations in each Fpn, where P is a prime number and N an integer greater than 1. So okay, it's so you may wonder, okay, but does such things exist? Yes, the projective spaces, Grossmanians, and so on satisfy this requirement, for example. And then he said, okay, so if you compute as algebraic geometry tells you the zeta function associated to such a scheme, it will give you something like that, where here it's the actual Riemann zeta function. He said, well, to define the zeta function of my scheme, but considered over F1, I kind of erase the zeta function and reverse what's here. So okay, it looks very ad hoc at first, but what is weird is that it's a zeta function over F1. It's a limit when p tends to 1 of this function. So here it's the Asservale zeta function. So here is the function associated to this scheme over Fp, such that the logarithmic derivative of that, it's the generating series of the number of solutions of x in Fp to the n for all n's in times that. So
sorry, can I ask a question?
Sure.
Do we know all schemes over F1? Have they been classified or?
Not that I know of. I mean, in what I know and what I've read, people showed that this example, in fact, satisfy the requirement are schemes over F1, and then they focused on computing the zeta function. But so far, no, I don't think it has been classified, and it's maybe because somehow the point of view evolved later, and that's maybe why people didn't spend much effort trying to establish a well-defined geometry over F1 and really say how the schemes should be. That's my guess, but I don't know the answer. But okay, so yeah, so Soulé was able to come to this formula, okay, which is here a first instance of the quest for characteristic 1, where you say p tends to 1. Obviously, it's first you take this expression, you have p as a parameter, and then you make p tend to 1. But the problem, if you want to go to the study of the Riemann zeta function, is that somehow the n1 that was appearing here in the previous formula is expected to be minus infinity. So you see when p tends to 1, you have p minus 1 to the power minus infinity. It looks very nasty. So what Kohn and Consani did in 2010, they reinterpreted the formula of Soulé. It's fact to say that when you adopt this notation, zeta n for this zeta function over F1, its logarithmic derivative, it's minus this integral, where here it's just a polynomial function that you require the existence for x to be a scheme over F1. And here the proof, so I don't have time to focus on it, but it's very easy proof. It's just like, it's to say that when you take the limit, it's here you have a sum, and somehow this sum is a Riemann sum. And when p tends to 1, it's just saying that the Riemann sum approximates the Riemann integral. So it's in fact really basic, fundamental, but basic statement on Riemann integrals. But then what was nice is that in this form, when you want to here not to have the function of a scheme over F1, but the Riemann zeta function, then you can say, well, instead of having here a polynomial function, maybe I can have something more complicated, and maybe this formula will work, whereas the previous one, it's hopeless. in fact, it is. So it's what I've written here in lines. It's the action is given by the distribution trace, the distributional trace of the scaling action of the Idle class group on the Adel class space. So that's what they proved in 2010. So you see, because in this story of Soule, which was okay, reinterpreted later, but still in this story there was this P10 to 1. It's one int that one should try to do something of characteristic 1. And that's what they did. So here it's finally the definition of an arithmetic site. Okay, so it's here this space, which is a topos. Okay, it's the topos and cross hat. I will give you the definition very soon. And then with Zmax, Zmax. So it will be, so here you must see that as a space, and here and this as a structure sheaf on Zmax as the structure sheaf on this space. And Zmax, where is it? It's Z union minus infinity, and you will have I say semi-ring, so you will have two laws. The first law on that will be the max law. So when you take two elements in Z union minus infinity, you take the maximum of the two. And then on the second law, it's the addition. And the semi-ringed, meaning that those two are monoid laws. And then you have the distribution and distributivity, sorry, of the plus with respect to the max. Okay, and that and the fact that it's somehow a sheaf, I mean an object in this topos. It means that you have an equivariant action of m cross here, just acting by the multiplication. Okay, so here it's something weird to do. I mean, from the start, from the first time we learn mathematics. Okay, we have the Z, the integers, and usually we see them as okay, as an ordered ring, like the first law will be the addition, the second law will be the multiplication, and then we have an order relation on that. And here it's kind of taking the same ingredients, but seeing them in a different way. It's we take Z, okay, we add minus infinity, but it's more technicality than something else. And the first law, we say, okay, the first law, it will be based on the order somehow, it's the maximum. Then the second law, which should, in our mind, act as a multiplication, it will be the actual addition. And then on that, we will make an action by multiplication, but since it must respect the maximum, it will, and so the order, it will be only an action by the positive and the non-negative integers. Sorry. And what was important is that okay, we can consider that, but what makes it really nice is that in fact when you compute the points of this space over R max, then you get the Adel class space, and in fact you get also the scaling action on the Adel class space, and hence since you have the scaling action, you are able to find again the link with the spectral interpretation with the zeros of the Riemann zeta function. So it was really striking, and here it provides a geometrical object for which I mean you can get your hand back on the spectral interpretation of the zeros. So okay, it was very striking. But first, I want to say some words, because I don't know if you are familiar with it, about what is a topos, because you see here I said that it's a topos. You should see it as a space, but it's not very explanatory. In fact, the topos were invented by Grothendieck for the purpose of solving the Weyl conjectures. And it was, he considered it as its greatest invention. In fact, it's one way to see it. It's that it's a vast generalization of space, and somehow it allows you to transfer geometrical instincts, geometrical technologies to more abstract context and to some categories somehow. And also something that it's fruitful, and Grothendieck was aware of it, but it will not play a role here, but it's very important as well, is that somehow topos is a mathematical environment on its own. It has its own logic somehow. I mean, logic in the mathematical sense, logical theory. And in fact, it's very important when you study the logic of topos, the internal logic. It could give you meaningful information. But okay, what is a topos? It's somehow, I said, the idea you should have in mind, it's kind of the inverse of the myth of the cavern by Plato. I mean, in the myth of the cavern by Plato, I mean, a simplest way to see that is that, okay, we are in the cavern, we see the shadows of the exterior objects on the wall of the cavern, and the whole point in what Plato advocates is that somehow we have to climb our way up and go out of the cavern. And here it's somehow the other way. It's to not try to go out of the cavern, but it's to look at all possible shadows on all possible caverns. Meaning what? It's meaning that when you want to study a geometrical object, instead of focusing on okay, my object is the set of points which satisfy this and this condition and so on, is to say what I'm interested in is only the functions on this object and the opens on this object. In fact, it's very profound, and if you think about it, it's the way somehow most animals perceives the shape of objects. It's that we don't know, if we look at an object far away, we don't know what the object is made of, but since we have by our multiple eyes, we have several perceptions of the same object. In our brain, we are able to somehow reconstruct the shape of the object. And here is topos. I mean, and that's the way I see it, is the way to do that mathematically somehow. And if you want to have a more technical statement, is that it is that a topos, at least a Grothendieck topos, it's a category equivalent to the category of sheaves over a site. And a site, it's somehow it's a category, but equipped with a topology. So, and to define a topology for categories, you just mimic what happens for the category of open sets of a topological space. So, but I won't get into the details. And when I say a point of the topos, in fact, it's a pair of adjoint functors. And to give you an idea that you must that you could keep in mind, if somehow you consider X a sober topological space, so sober, it's a technical condition, don't worry about it for now. You take the category of all sheaves on this topological space, and then the points of X, so here meaning the points as we intended in topology. It's in bijection with the pairs of adjoint functors, where here you have one functor, which is the direct image, it's the skyscraper sheaf. I mean, it's the functor which to a sheaf associate the skyscraper sheaf at the point X. And here the inverse image functor is the functor which to a sheaf on the topological space associate the stalk of the sheaf at the point X. So, and okay, so here somehow it's you see this notion of point of a topos, since topos is just category theory with okay, more conditions, but it's just a category. It's a way to transfer a geometrical concept into categories, and somehow it will allow us to be able to find this space that we were looking for. So here for the arithmetic site of Noncommutative, first you define what is the site, okay, and here it's the category where you have only one object, okay, and the arrows are indexed by the the positive integers. And the composition law of the arrows, it's given by the multiplication of the positive integers. And then the topos you are considering, it's what we call the preshift topos associated to n. So it's just the functors. It's the category of functors from n star to the category of set. Okay, and here what I did is that I mimicked the construction, but here I mean one of the question that I had is okay, here you talk about positivity, but for Gaussian integers it seems hopeless to rely on some positivity of some sort. So here you have to allow all of the Gaussian integers, and somehow you consider the preshift topos associated to zi dot, as I said. So it's only one object. The arrows are indexed by the Gaussian integers, and the composition law, it's the multiplication. So really it's the same as Kohn and Consani, but for the Gaussians, and you don't care about the positivity because here in this context, it wouldn't make any sense. And what you can do when you enter into the details is that you can compute the category of points. So Kohn and Consani did that, is that somehow the category of points of this topos is the totally ordered groups isomorphic to non-trivial subgroups of Q, Q plus. And I did the same in my study for the Gaussian integers. When you want to compute the points of that, in fact, you find that it's the category of sub-zi modules of Qi, which is weird because here points, it's not a set anymore, but it's a category. So it looks weird at first. In fact, I proved this in my article. We can generalize that for all principal number fields. So, but then, as I said, Kohn and Consani considered Z max, so the structure sheaf, and you understand that for Z max, well, here it's you cannot get rid of the order like this because it's essential. I mean here, so yes, what I can say is that okay, okay, yes, so yes, I was going a step earlier. Sorry. So you consider the isomorphism classes of this set, those category of points, and in fact, you found that it's a set. In fact, here it's described as a quotient of the finite adels. So it's good and it looks nice. It was a nice hint for them, I guess. But you were missing the Archimedean place, so you are not completely satisfied with that. And me, I was able to mimic their proof for the Gaussian integers, and you found really the analogous statement. But here, as I was saying, okay, for the structure sheaf that they put, then it was Z max. So here with Z max and plus. So here, one thing that I forgot to mention, why is the law max very important? That when you take max, I mean, it looks so stupid said like that, But when you take max of A and A, well, it's A. So somehow it says that this law, max, this law is idempotent, and hence the characteristic one somehow. Characteristic one, where you know in characteristic one you would ask for somehow A plus A plus A is equal to A. So of course a characteristic one cannot happen in the world of wings, because that it would say you just restrict yourself to the zero wing. But if you allow yourself to move to semi-wings, where here you don't require that this first law is a law of group, then it allows for you to take an idempotent law, and then it does something that you want. But my problem was when I was thinking about that was what can we do for the Gaussian integers, because you don't have a maximum or a way to say canonically that's to imitate the maximum. And in fact I found a solution, which was to consider what I denoted by this. So but it will be better to see that on a drawing. Okay, so what happens is that when you take Kohn and Consani site, arithmetic site, and you look how, so here you have Z max here, okay, so the elements of Z max is the integers, and you look at how the positive integers act. It looks like this, but in fact you can do something similar and prove almost the same results as Kohn and Consani, where you get rid of the positivity here for the actions, and you look just at intervals, but symmetric with respect to zero and with integers endpoints. And here you see the action of -1 is trivial, but here you can add by 3. Okay, and once you see it in this way, then the generalization to Gaussian integers looks more natural somehow. Is that here, instead of considering this first interval where it's just -1 and 1, so -1, 1, here it's just the convex hull on the line, okay, on the real line of -1 and 1. And here, what the object that you look, it will be this square, which is the convex hull of 1i minus 1 minus I, which are the units of the Gaussian integers. And then you will act by multiplication by a complex number, but here it will be just by a direct similitude, in fact. So it will give a scaling action by the module. I mean, you will scale by the module of your complex number that you multiply by, and a rotating action by the argument. So that's what I did, and that's why I proposed somehow for my for the arithmetic side for the Gaussian integers, I considered the semi-ring generated by all the squares. I mean, this square and all its rotation. I mean, rotation by a complex integer. Okay. And so, okay, here when Kohn and Consani studied the points over Rmax, so it's really it's the same, if you want, as in algebraic geometry as the point over a given field. And then they recovered, as I said already, this Adel class space, but here you see it's not the finite Adels anymore, it's really the total Adels. And here it's a technicality. It really means that it's like in algebraic geometry. And what I did somehow is that I considered this arithmetic site. I considered the summering generated by the squares. But here rotated, you allowed the rotation by any complex number that you wanted. And for the laws, yes, it's, I didn't specify, but it's the convex hull of the reunion and the Minkowski addition. It makes that into a summering, and it made that also into a summering as well. And I said, well, when I want to look at the point of this arithmetic site into that, well, I had to impose a technical condition, which was that somehow the morphism at the Stokes were given by a direct similitude. It was kind of ad hoc at first, but okay, if you accepted this first definition somehow, then I was able to prove a theorem which was kind of analogous to the one of Kohn and Consani. I got the identification of this set of points of this new arithmetic site over this kind of analog of Rmax plus. Okay, so over this summering of convex polygons. That it was identified with this quotient of the Adel class space, but here the Adels for Qi. But here it was not so much the quotient. I wanted just to have the spectral interpretation of the Dedekind zeta function. But in fact, it's much nicer because here, when you do this, which in fact looks quite natural, even if I hope I have to have time to speak about that, but in fact, we can prove that this, looking at this, is quite natural. In fact, you get not only an interpretation of the zeros of the Dedekind zeta function, but the zeros of a whole family of equal functions that are related to the study of the repartition of angles of Gaussian primes. So it's quite nice, but it was a surprise, in fact. And here it's the technicality, but I don't have time to explain this. Here, so I will skip some things, but here, as I told, I had to impose this condition that it was a direct similitude, and it was bothering and not very satisfactory. So then Kohn made a remark to me, so I don't have the time to. I don't have time to explain the details, but what he was able to prove somehow, it was that with a careful geometric reasoning, in fact, and reasoning about those convex squares and how they behave, and studied the summering structure on that. It was that in fact the definition is intrinsic. And if you want, if you have a question about that, I could explain that to you later. But then he asked me a question, and I was able to improve. Is that one could say that okay, I take these squares and then these convex polygons that are symmetric with respect to the action of the units. Well, okay, it's nice, and you prove results that relate to arithmetics and so on. So somehow it works at some point, but it seems kind of far-fetched. How is it natural for arithmetics to talk about convex hulls? It looks weird. I mean, it's not that weird because in archive geometry they also talk about that. But at first, when you arrive in arithmetics, it looks weird to that. So, in fact, this ZI-conf, so it's the summering generated by the squares. It's a solution of arithmetical universal problem. So what is, I will try to explain what is this universal problem. Is that when you look at the quotient zi by its units, so zi quotiented by 1i minus 1 minus I, in fact, you can do as Krasner did. You can define an hyperaddition on that. So in this way, you take z1 time the units plus, so the Minkowski, the Minkowski sum, z2 of the units, and you quotient by the units again. And then what you prove is that when you have, so you start from this, because in fact we do all things with up to the, we consider the units as symmetries. So since we do that always up to the units, that's why you start from zi over the units, okay? And if you go to some semi-ring that has some properties, so that is conservative, I don't have the time to explain, but okay, and such that the laws of this semi-ring respect some properties. So it respects that the second law of your semi-ring, okay, it's somehow given by the first law on your semi-ring, but when you do the sum, okay, on this hyperaddition that you define over zi over uzi, and the result is that okay, when you have such a map, okay, you can always factor. So it's really striking. And here the map going from the quotient to the icon, it's to given z, you associate z time and the fundamental square. So it's the square somehow that has for vertices z, I, z, minus z, minus iz, okay? And the really striking part was that, okay, it's when it works, this semi-ring of convex polygons that looked kind of fallen from the sky at first. Well, it's something very natural in the world of semi-rings. So I don't have the time to. I mean, just one thing, because I find it funny, but I will not have time to go much into the details after that. But it's when here you have an idempotent semi-ring, which is conservative. So here the conservative part, meaning that if you have AB equals AC, okay, it means that A different from 0, then it means that B is equal to C. So, and here it allows you to show, in fact, that the map, so Frobenius, so raising to the power n. So here it's there's no trick. It x times x times x n times. In fact, it's an endomorphism, which is something really weird. And normally, the fact that it's an endomorphism, it only happens for in characteristic P when you fix the characteristic and so on. Here, when you work with an idempotent semi-ring, it works for all positive integers. And for example, the way that you prove for n equal 2, it's as I wrote upstairs, is that if you compute that, you use the fact that your ring is idempotent, then you find that a plus b times a square plus b square is equal to a plus b times a plus b square. And so you can, because your semi-ring is conservative, you can find that a square plus b square is equal to a plus b square. So that's the thing that all our undergraduates dream of. But then, okay, you use that and many other things. And when you use that, in fact, the idempotent part of your semi-ring, it makes the convexity appear naturally. and that was something nice. Okay, it's here. If you want, you see when you take Z, okay, an element which is in the convex hull of some of the of the squares defined by Z1 to the n, then it's imaged by phi because of all the assumptions that you made on phi. Okay, so because it respects the Frobenius and the Frobenius behaves in this way, and because phi respects this weird thing that when you multiply, then it's given by the sum, where you sum over another hypersum, then it makes that the image of phi is less than the image of Zi, of the Zi's, and it makes that somehow only the convex hulls matter, which is a really striking fact. So here is the proof, but I don't have time to expand on that. So okay, it was, so okay, here it's, I recall the universal problem. So it was very nice because it says, okay, and the structure shift that I put was in fact, so here's the proof, was in fact an actual one, okay? But now when you want to move to other number fields, so for example, Z square root of 2, I mean, at first when you looked, if instead of going for the Gaussian integers, I first went for Z square root of 2, then I would have thought that, okay, maybe a way to mimic what Kohn and Consani did was to take Z square root of 2R, as I said. So I take, I place myself in R2, and I look at the points such that the first coordinate is because you have two embeddings of Q square root of 2 into R, you look at the first coordinate is the image of, I mean, it's an element of Z square root of 2 by the first embedding, and the second coordinate is the image of the same element of Z square root of 2 by the second embedding. And then you can take the max, so the max coordinate by coordinates and the plus coordinate by coordinates, and it would look closer at what Kohn and Consani did. But since I studied the Gaussian integers, and because the units here played a huge role, this for the Gaussian integer, the 1 minus 1 I minus I, and then here it suggests that the units of this square root of 2 are in fact the totally positive units, so it's the units that are positive and under both embeddings should play a role and should be important, and so it dismisses this first try. And in fact, it says that really the totally positive units should be something really to be considered, and you should really try to see that as the symmetries of the structure shift that you want to put on the space that you, the topos that you want to consider to build other arithmetic sites. And so one way to, so here it's a list of reasons that in fact the totally positive unit and their multiplicative action in fact has already been quite studied in algebraic number theory. First it's the Shintani unit theorem, which is really important for building in fact other arithmetic sites, that this totally positive orthant, so it's the orthant of totally, I mean the coordinates are all reals, but all are positive reals. And in fact, you can make, when you fix a number field, you can make the totally positive unit of your number field act on that. And the thing is that you can compute a fundamental domain for its action. It was done by Shintani, and it says that it's a finite union of a polyhedric cone. So it's something quite nice. And in fact, it was used to study the values of the Dedekind zeta function at negative integers. And it has even more recent developments. And here, the thing I'm trying to do right now is to give a toposic view. So by the means of arithmetic side, building arithmetic side, a toposic view of this action of the totally positive unit of a number field, and maybe establish some links with previous works that has been done. So maybe I don't know yet, but one could hope the study of values of the Dedekind zeta function, or maybe have a link with Stark-Shintani conjecture, which is somehow a way to try to approach explicit class field theory. So here I explain how I do it. Is that somehow you consider again you consider the totally positive unit, and I mean, here instead of having squares, you will have kind of a fine by part hyperbolic domains, and you will play with that somehow, at least for this square root of 2. For others, it's I don't have a view for all number fields. So, but at least for this square root of 2, you will play like this. And okay, so I will stop there, but here it's a technicality just to make the link with some of the stuff that Kohn and Company did, the S-algebra, but something that I found kind of relevant if you know Boscon systems, and especially the articles of Lacan, Eshveyev, and Trifkovic, and Lacan, Eshveyev, and Mersenne. They built Echo pairs using also those totally positive units, totally positive integers, and so on. And I mean, they found conditions for which you find again the Boscon system for general number fields, and I mean it gives the taste or the hint that somehow our constructions, like I mean it's the same technical. I mean, of course, it's not about. At some point it diverges, but at the very beginning, when you want to construct your basic objects of your theory, it's the same kind of constructions. So it suggests, I don't know, maybe there could be a link with Boscon systems, or at least that you could get an inspiration from Boscon systems to build more arithmetic sites in the future. And I will stop there because I already went over time. Sorry about that. And if you have questions, I would be very happy to answer.